So there are three methods for evaluating limits, and I'm going to show you the most direct ways or different ways to approach problems to know what do I need to do. Now, we have already looked at some pictures of graphs. We've already looked at that. And we've looked at quite a few tables as well. But what we're going to look at the most and what you're going to use the most as we go through this section in this chapter is our algebra. Now, if there's anything that's going to trip you up in calculus class, it's going to be your algebra skills. So hopefully you have a good foundation, or you are reaching out for help if you don't have that firm foundation to help you to be successful with your calculus. Algebra skills are what's going to kind of cause a hurdle for you. So hopefully we can kind of clear up some misconceptions. I can remind you of some things as we go. So, a couple of different ways that we are going to use algebra. There's going to be two different ways that we approach it. One, or the first way that you want to approach these limit problems, especially when you go into the homework, is you want to just use your direct substitution. Whenever I'm working a limit problem, that's the first thing I'm going to do. I'm going to direct substitute or plug in for x, see if it works out for me, because direct substitution could work. Now, it hasn't worked in the previous problems, and there's a reason I picked those kind of problems where they were undefined, so we could do that approaching and really get that definition of the limit as x approaches. But that's not always the case. We're not always looking at undefined functions. And so let's look at this here. Let's look at this first one. It says, what is the limit as x approaches 1 of 2x squared minus x minus 1 all over x minus 1? So the first thing that I'm going to do is I'm going to direct substitute. I'm going to plug it in. Now, when you take the limit, you no longer write your limit notation. Remember, I'm going to be very particular about your notation. I want anything that you present to me to be beautiful. I want it to look like what we have been doing. Not just because I want you to be like me, but because I want you to learn a process and a way that's going to carry you through other courses or through other concepts. And so this is what you need to learn. When you write that limit notation is like an operation. This is your instructions telling you to take the limit as x approaches 1. So if I now go to take the limit after the equal sign, I'm no longer going to write limit because I am now taking it. So this would be 1 squared minus 1 minus 1 all over 1 minus 1, and I'm just plugging in for all these little x's at the value of 1. I'm going to evaluate that, so that gives me 2 minus 1, which gives me 0 over 0. But 0 over 0, that's still undefined. It's going to work eventually. I'm going to show it to you. So since that didn't work out, you have to think of algebra. What algebra skills do you have? Or I always like to kind of tools in your tool bag to help you with this. And so we're going to restart. And we're going to say the limit as x approaches 1 of this function. Now, when I see a quadratic function like that, I'm going to try and factor that. Remember that when you're factoring, we are going into the two things that were multiplied together to give you that quadratic. Now, if you need additional resources with factoring, reach out, let me know. I'll help you with that. This actually factors into, let's see, 2x and x. The signs are different. And what will multiply to give me 1? That'd be 1 and 1. And then the bottom's just x minus 1. Now, the reason I want to factor that out is because now that I have everything being multiplied on top and everything being multiplied on bottom, I can cancel. I cannot cancel because I see it here. That is not factual. I can cancel it once I get to multiplication of parts. So this now cancels. And my new function, have we taken the limit? No. So I have to write limit as x approaches 1 of our new function that's been reduced of 2x plus 1. Now I can plug in. And so once I plug in, I'm no longer going to write my limit notation. So that would be 2 times 1 plus 1, which gives me 3. And so following my line of equal signs, I would say the limit as x approaches 1 of my function is equal to 3. And these would be all the steps that I would need to see. Limit notation must be written If you are missing a limit where it needs to say limit, that's -1. If you overwrite limit because you're scared of getting -1, that's -1. All notation needs to be correct for this entirety of the course. I'm warning you now. I'll warn you through each lecture. So you can see, to sum up this problem, we did a direct substitution first. We tried to evaluate it. It did not work out. Now we're going to try our algebra skills, and we had a factor. Then we were able to plug in and get it. So let's do another one. This says the limit as x approaches 0 of x squared plus 5x minus 6 all over x squared plus 3x plus 2. So the first thing I'm going to do is I'm going to direct substitution, plug it in. That means I am now taking the limit, so I'm not going to write my limit notation. So this would be 0 squared plus, that's a 0, times plus 5 times 0 minus 6 all over 0 squared plus 3 times 0 plus 2. Well, that's 0, so I get -6. That's 0, so I get +2. So it gives me -3 for the result. Direct substitution worked. I don't have to factor it. Now, don't get caught into that rut of going, oh, I got to factor, and don't overwork the problem. Yes, they both had quadratics, and yes, we could have factored them, but that was not necessary because this problem can be evaluated. So when you're looking at limits, what you want to do first is do a direct substitution, and then if that doesn't work out, pull out some kind of algebra skill to help you with that. Now, previously, 2 examples ago, I alluded to something in an illustration, and we're going to revisit that here and pick up some new notation. So let's look at one-sided limits. When you're looking at a one-sided limit, they're known as right-sided limits and left-sided limits. And you guessed it, there's a new notation for that. So for right-sided limits, we're going to say the limit as x approaches c. Okay, not new. But right here on the c, I'm going to put a little plus sign in the right-hand corner, although it's an exponent. Having this plus sign in the top right-hand corner is telling us the direction in which we are coming. That's why we didn't put it out front and mistake it for a positive or a negative value on our number line. We put it in the top right corner to show us the direction in which we're coming from. And so we would say if f of x is equal to capital L, our limit. Again, you want to follow all writings that I do. If I write limit in lowercase, you should write limit in lowercase. If I write a capital L, you should write a capital L. These are universally known definitions and notations that are going to carry through other concepts. So if you're one of those people who write in all caps, this is not the time. I'm trying to save you now. Okay. If you're one who just always does it a certain way, even though someone else has written it like that, I would again advise you now, and I'll remind you again as we move through concepts, write it as we write it, because that's going to carry you through these concepts, chapters, and other courses. So this means if we are coming from the right side, that's the direction that we're coming from, we are going to be moving left, but coming from the right. And we're going to write this down, and I'm going to jump over that illustration and show you what we're talking about. The left-sided limit notationally is going to be equal to the limit. Again, I always write limit in cursive. It's just so my L doesn't turn into a 1 in years and years of writing it. That's what kind of flows out. And so this is x approaches c from the left. It has a little negative on the right-hand side of f of x. And again, this is your notation, but also your directions or your instructions. Is equal to capital L, and that means if we are moving right, but we are coming from the left. And so again, left-sided limit, that means we're coming from the left. And right-sided limit means we're coming from the right. So this would be your left and your right, just like you already know. And so just notice the positive and negative signs up in that top corner. And why would we even break this apart? Why would we even look at the left and right hand limits? Well, what I want to do is let's jump back to that illustration that we were just looking at previously in this section. So here's that illustration we were looking at earlier. And earlier I was just kind of show you how it was y values and you're approaching. Let's look at the other stuff that is here. So you can see if I move this x value and I'm coming from the left, see how we're on the left-hand side, we're moving towards our c value. This says as x is approaching 2 from the left, notice its notation, as x approaches 2 from the left, and we're getting closer and closer, we're getting close to a value of 3. Now, here's where we left off and what I couldn't really say last time we did this illustration. Notice if I move this x value over here and we move it from the right. So as x approaching 2 from the right, we're on the right-hand side of our c value and we're moving closer and closer and closer to it. As it gets closer and closer, but not on it, because remember it's approaching. Oh, sorry, it's jumping. You can see it's actually approaching -1. Because of this disconnected, we're going to talk about that again. Because of this function that's disconnected here, it's not continuous. We can't smoothly write it. We'll talk about that. The fact is, we are approaching a different value on the right-hand side because, again, it's not where we are straight up at it. It is what is it are you approaching? So with this one, as we are approaching this value, we are getting closer and closer and closer to actually -1. And so this is where your left and right hand limits are going to come in handy with functions such as this. But I want to show you this notation right here and how it's approaching from the right side or approaching from the left side. And I just think this illustration helps you to kind of see that as you go. So let's jump back to the notes and let's apply it to some specific examples. Here's our examples. So let's look at this example here. And it says the limit as x approaches 0 of the square root of x. Now, you're going to have to remember previous courses, previous foundational concepts. That's why you'll notice if you took algebra, you took pre-cal, we emphasized on parent functions and transformations because having a base knowledge of your functions is what's going to help you as you work with different functions, equations in this course. We don't need to go and look up everything. We need to know our basics and then build off of that. And so everything we're going to do, we're going to build. So with this one, let's look at it. If you remember that parent function, square root of x, it started at the origin and then it looped up something like this. So if we look at this function and we say, what is the limit as x approaches 0 from the right? Well, when we approach it from the right, that means we're moving this direction right. We're getting closer and closer, and we say, what is it approaching as we get closer and closer to 0 on our x? And that thing would be approaching 0. Now, if we look at the limit as x approaches 0 from the left of this function, the square root of x, well, you'll notice nothing exists over here on the left. There's nothing that I can approach on to actually get there. We don't have a left side of this limit. And so what we would say is, what is the limit approaching from the left? It doesn't exist. I'm not going to make things up. Okay, we are looking at which is approaching and saying, okay, we are approaching a value, but we're not just going to pull things out of left air, like left air. We're not going to pull things out of thin air and go, oh, well, we're going to say it's approaching this, even though we don't have anything there. We need like some factual evidence to go with it. So sometimes when you're looking at the left and right limits, you have a left limit, but you have a right limit, but you don't have a left limit. And that's okay. And that's why we could break apart this larger concept of limits into lefts and rights. Let's look at the next one, because it's always these kind of odd looking functions where things happen. And so as it says, evaluate the limit as x approaches 2 from the left of x minus notice these brackets here, x, and then look at the limit as x approaches 2 from the right of x minus these brackets, x. Now, if you don't remember what these types of functions are, let's kind of review that. It is a function that is not used super often, but typically when you're looking at these functions, it has like a double bracket going on when it's drawn. So it's kind of interesting. It's known as a step function, or the greatest integer less than or equal to that function. If you've had me in a previous course, you may have heard me say round down when you're looking at it. And so what it does is anything inside those kind of double brackets there, round down to the nearest integer. Now remember, integers are -2, -1, 0, 1, 2, 3. It's all those really nice numbers, no decimals, no fractions, but it does include negatives. And so this is what this function looks like. And so if we were looking at what is the limit as x approaches 2 from the left of this function, okay, well, let's look at that. Coming from the left and approaching 2, so if I start way over here left, I go up. I'm getting closer and closer and closer to 2. As I get closer and closer, it looks like I'm approaching a value of 1. And then if I look at and say what is the limit as x approaches 2 from the right of this function, well, let's come from the right. From the right, I'm coming down this way. And I'm coming down, and you want to look as you get closer and closer and closer to 2, it actually looks like I'm getting closer to a value of 0. So again, case in point, your left and right limits are not always going to be the same. Now, if it was a graph, if it was a function like this, you're going to be given a graph. I don't want you to freak out. I know some people are already concerned, I can't use a graphing calculator. You don't need it. You are very smart. You can do this without a graphing calculator. But there are functions. I'm going to give you a graph because I want you to understand from a graph or from a table or from a function what is going on and can you get that limit. So we're going to see it in all those facets. So don't stress. You should know the previous one. You should know square root of x and what it looks like. But with this x minus the greatest integer function of x, you're going to be given a graph. So I wanted you to kind of relate those two and see what's going on with that. This leads us into a theorem. This is theorem 1, and it's the one-sided limit theorem. And the one-sided limit theorem says this, that if you have the limit as x approaches c of f of x equal to L, if and only if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right, and let me move this downward so we have a little bit more room for all of it. So the limit as x approaches c from the left of f of x is equal to the limit as the x approaches c from the right of f of x is equal to L. Now we're going to write that down and pause the video. Then let's start up again. Looking at this, how you read this, when you have an if and only if statement, if you are choosing a STEM-based major, you're going into engineering, mathematics, computer science, anything like that, typically you're going to have to do this entire calculus sequence, and you might even need like a foundations of math course, some kind of proofwriting course, either to get you to an 18-hour mathematics minor or to help you into introduction to your junior and senior level math courses where you begin to prove things. So a lot of times through this course, when we get to theorems, we're going to do some shorthand on top of it. And so I'm going to show you a couple of symbols with this one, and it's going to help us to understand the theorem as well. When you see statements like if and only if, what this refers to is really a double-sided arrow. And so I'm going to draw a double-sided arrow on top of this, because what this is saying is if and only if, and it's going to go in both directions, saying if I have a limit, if I have, go with left and right again, if I have this information here, that I have a limit as x approaches c. I just looked at it. I found when it was approaching, consider your tables and graphs we just did of f of x. Then I know the left and rights both went to that limit. Now, it does go in this direction from the left to the right. That's this side of your arrow. But it also goes the other direction. So if we start it with the right-hand side and say, hey, looking at the limit as x approaches c, it's L. Looking at the limit as x approaches c from the right, it's also L. Those two left and right side limits are the same. Then we can go backwards. We can conclusively say that the entire limit as x approaches c, who cares left and right, is also equal to L. So that's why when you see theorems, corollary statements that we make and we say if and only if, that's why we put this double-sided arrow on top of it, because it tells me whether I start with the beginning or the end, we can go either direction in that theorem. And that's really great that we can start on either side. That gives us some facts to work with and some other information. So it's going to pay off for us. So we have that theorem. If we have a left and right limit equal to L, then we can conclusively say that's the limit. Or if we have the limit, we can already state the left and right. Now, if there is any additional information that comes out of a theorem, then we have it by another name, and we call it a corollary. And so in this next part, we get a corollary from that theorem, and it says, if the limit as x approaches c from the left does not equal the limit as f approaches c from the right, then the limit does not exist. So let me mark out some keywords here. If. So here's how this one's going to work. So if this first part is true, another thing that we would say is, kind of a shorthand is we would do an arrow right here over that then statement. This would signify that you would have to start with what is given, and if we can get that part to be true, then we can make the assumption of this part on the other side. Now, you can notice that this arrow does not go the other direction. We don't say, okay, the limit doesn't exist. That means the left and right aren't the same. You start with the left-hand statement, and it can move to the right. So a lot of times with theorems or corollaries, you're going to see if and then, or you are going to see an arrow as a shorthand notation. So I'm going to leave that arrow in our notation because I really think that helps us to understand these corollaries and theorems, especially in our notes. But also it's a shorthand for it. If you were writing this out in a proofwriting course, you could use those arrows accordingly. So it says, if the limit on the left and right are not the same, then we would say that the limit does not exist. And so in unique functions or kind of ones where weird things are happening, this is going to be our proof, our facts, in order to support our answer. In math class, we always say, show your work, show your work. Well, as we move into calculus, a lot of the work you're going to show is not showing 2 + 2 = 4 and you worked out those steps. It's a matter of proving the facts that led you to that answer. And so instead of just saying the limit does not exist, you would have to say, what is the left from the right? Here it is, teacher. Here's the limit from the right or the left. Here it is, teacher. And then you would say, therefore, because I've shown you the left and right limits, this limit does not exist. And so what I want to do is I want to consider this function here. It says, consider f of x equal to the absolute value of x minus 5 over x minus 5. So a little teacher bonus, I'm going to show you how to break apart this function and how we could actually graph it. So when you're considering this kind of function where you have the absolute value of x minus 5 over x minus 5, it is actually a piecewise function. It is one that you'll notice 5, okay, I can't plug in 5 to get division by 0, but consider the numbers before it. If I were to plug in 1 into this, I would have 1 minus 5 on top, which would be -4. Absolute value of -4 would just be 4 all over the bottom, which was negative. So anything I plug in smaller than 5 on top turns positive, but on bottom still stays negative. And so it actually just gives me a line down here at -1, because it's the same thing. Something over itself is 1. Having that absolute value there is just going to be changing the sign. When I get greater than 5, 1, 2, 3, 4, 5, I'm going to jump up here to +1 because something over itself is just 1. And I have no value actually at 5 because I have division by 5. So this is what this graph looks like. So if I go into this and I say the limit as x approaches 5 from the left and the limit as x approaches 5 from the right, of what function? This function here, the absolute value of x minus 5 over x minus 5. Well, that would be equal to, coming from the left-hand side, we look like we're getting close to -1, because remember, it's a y value. And so I would say the limit coming from the left is -1. If I look at the bottom one, the limit as x approaches 5 from the right of this function is going to be equal to, okay, coming from the right, it's getting closer and closer to +1. And so the limit coming from the right is +1. So if I am, in a general sense, saying what is the limit as x approaches 5 of this function, because, you know, we plugged it in, we got undefined, I would say this does not exist. In order for you to have a limit based off that theorem, or more specifically the corollary, you have to look at the left and right hand limits, show that work per se, show your work, and then you could clearly state this. So this is going to be a downfall of an online homework assignment, and the fact of it's probably just going to say, what's the limit? And you say D and E, okay, done, moved on. But when it comes to exam purposes, and I'm looking at your scratch work, because I'm a math teacher, I'm going to grade your scratch work, you're going to have to show all information that's circled in pink here, because you're proving why you got it. Why do you understand that that limit does not exist? Now, I told you in a previous part that as we look at functions, we are going to have to do a little bit more with them. And so that's where I want to pick up next.